All right, let's take a look at the questions from section 2-3. So, want to look at a couple systems of equations. First, I want to show that, all right, I mean, we don't know how to solve these things analytically, but we do have the means to verify solutions that are given to us. So, let's go ahead and do that. So we're given basically a solution for x, a solution for y, given as a vector. So basically, this top row is x of t, bottom row is y of t. Um, the equations I'm given are first order, so I can um, take the first derivatives of each of these and verify. So first derivative of x is going to be 3/4 times 2, so 3/2 e to the 2t, plus 3/2 e to the negative 2t. All right, and then y prime is going to be 1/2 e to the 2t and minus 3/2 e to the negative 2t. All right, so now let's verify our equations here. So x prime is equal to uh, x prime is equal to 3/2 e to the 2t. Actually, let's just do this. Let's figure out x plus 3y, and we'll verify that against our derivative. X is 3/4 e to the 2t minus 3/4 e to the negative 2t plus 3y. So plus 3 times y. So plus 3/4 e to the 2t plus 9/4 e to the negative 2t. All right, if I start collecting like terms, what do I get? So e to the 2t, I get 3/4 plus 3/4. That gives me 3/2 e to the 2t. So that term checks out. 9/4 minus 3/4 e to the negative 2t. That gives me 6/4 e to the negative 2t. That's also 3/2. So that solution seems good. What about x minus y? So x is 3/4 e to the 2t minus 3/4 e to the negative 2t minus y. So minus 1/4 e to the 2t minus 3/4 e to the negative 2t. And combine like terms again. So 3/4 e to the 2t minus 1/4 e to the 2t, that's 2/4 or 1/2 e to the 2t. Negative 3/4 minus 3/4 e to the negative 2t, that's minus 6/4 or minus 3/2. So verified. So our solutions are good. Actually, we should probably check the initial conditions as well. What happens when I plug in 0 for all my t's um, in my x solution? Then I get 3/2. Oh, sorry, that's x prime. 3/4 minus 3/4, 0, good. And then y naught? That would be 1/4 plus 3/4, that's 1. Okay, so both of these look, everything checks out, initial conditions and the functions themselves. All right, so parts B and C, we want to use Euler's method, and I asked you to use technology for this. I couldn't find, I had a lot of trouble finding a technological resource that approximated this specifically using Euler's method. So I wrote a code for it. So let me make the modifications here. So for this first part, I want to use a step size of 0.5. So I'll set that up. I want to approximate to 6 seconds. So I think I need 13 steps. Initial value for t is 0. And my initial values for x and y are 0 and 1. Already have that in there set up. Okay. Now I have to enter the differential equations. So dx is equal to x plus 3 times y. And dy is equal to x minus y. All right. Now, if I run this, I should get all the information I want. So with that half second, or yeah, t equals 0.5 step size, let's look at what I got here. So let's write down the order of triples I got. So I get 2, and then my x values are 12 and 4. 2, 12, 4. When time equals 4, I get 192, 64. Looks like I'm getting integers. And finally, at time equals 6, I'm getting let's just give up the delusion trying to fit that on that one line. Okay. So part B is right here. So 3072, 1024. Okay, so that is for part B. Part C wants me to make the same approximations, but with a smaller step size. So I'm going to tighten this down to 0.1, which means I need to take more steps. 61 ought to do it. But the initial equations are the same, initial values are the same. So let's go ahead and rerun. All right. So now let's see what we have. So at 2 seconds, okay, so my numbers are very, very different. So at 2 seconds, I have 28.8, 9.6. Then at 4 seconds, I have 1102.3 and 367.4. And at 6 seconds, so wildly different behavior here. So 42,261 and 14,087. So same equation, just tightening up the step size really changes things a lot. So leads me to believe that, I mean, in general, we say that smaller step sizes lead to better approximations. And since these are so different, I'm going to assume that my first set of approximations is far worse. Only way to know that for sure is to go to Desmos, and I want to use that again. So now let's go ahead and define our equations. So f of x equals 3 over 4 e to the 2x minus 3 over 4 e to the negative 2x. And then g of x equals 1/4 e to the 2x plus 3 over 4 e to the negative 2x. All right, so what's f of 2? What's g of 2? All right, so at these values, now I'm led to believe that neither one of my approximations are all that good. So why is that the case? I mean, I'm using Euler's method with a pretty small step size. So a couple of things to talk about here. One is that Euler's method is kind of the simplest method we have. Even if we make the step size super small, what do we look at when we use Euler's method? Well, we're looking at the first derivative only. And when we look at a step, we're only looking at the value of the first derivative at the left end of each step. Compare that with Runge-Kutta. When we look at Runge-Kutta, especially fourth order, you're looking at first and second derivatives, and you're looking at what those values of those derivatives are at both the beginning point and the ending point of each step. These are exponential functions, and they grow very quickly. And not only is their rate of change very high, those rates of change increase at increasing rates. So the larger t gets, the more rapidly x and y are going to increase. So even our better approximation is off by, see, at t equals 2, x is about 41. I said that it was 29. So off by about, a third, by about 30, more than 33%. We'll see how that compounds as we go further. F of 4, G of 4. So F of 4 is, so X is 2235. I don't even have half of that. So again, we're seeing how these errors compound. The rates of change that I'm capturing from step to step, even in my better approximation, they aren't capturing what these equations really do. And that we should see that even worse here. So yeah, the X value at 6 seconds should be 122,000 or so. We're about a third of that. And the Y value, we're far less than a third of that. Actually, no, it's not true. We're a little bit more than a third of the 40,689 that we should have. So yeah, I think that the two biggest sources of those error are, yeah, this how simplistic our method is. I mean, with all due respect to Leonhard Euler, it's a very, very old method, and it's very, very simple, but it's meant to be. It was meant to be done by hand. But also because of that reason, it doesn't capture everything that you'd like to capture. All right, so let's look at another one. I'll go back to the slideshow to talk about number 2. So let's kind of run through the same paces. So this question here, so x prime equals y. So same kind of thing, we're going to verify that we have the solution we're offered is true. So let's find these derivatives. So x prime of t is equal to, I believe we're going to need product rule for each of these. So let's handle the exponential first in each of these. So negative 1/3 e to the negative t sine of 3t plus 3 times 1/3 e to the negative t cosine 3t. All right. Now let me make sure I have enough room to do the rest of this. Okay. Negative e to the negative t cosine 3t minus 3 e to the negative t sine 3t plus 1/3 e to the negative t sine 3t minus e to the negative t cosine 3t. Okay, so I believe that's my derivative of both x and y. So does x prime look like y? That should be easy to check. y is e to the negative t cosine 3t minus 1/3 e to the negative t sine 3t. Those look identical. I have the terms flipped, but they're fine. Y prime equals negative 10x minus 2y. Okay, let's find minus 10x. So minus 10x would be minus 10 over 3 e to the negative t sine 3t minus 2y. So minus 2e to the negative et cosine 3t plus 2/3 e to the negative t sine 3t. All right, does that look like y prime? Does anything combine? Well, I have 3 terms here and 4 in my derivative, so I didn't check if anything combines there. And they should. All I have is e to the negative t's and cosine 3t's. So let's do this. In this top line here, what is my coefficient of e to the negative t sine 3t? It'll be negative 10/3 plus 2/3. That's negative 8 over 3. Is that what I have down here? Negative 3 e to the negative t sine 3t plus 1/3. So negative 9/3 plus 1/3, that's negative 8 over 3. That matches. What about the cosines? I only have one term in my top line here, negative 2 e to the negative t cosine 3t. So down here I have negative e to the t cosine 3t minus e to the negative t cosine 3t. That's negative 2. So both of these look fine. I should check the initial values again. X not equals 0. That's true. Sine of 0 is 0, so everything else will get annihilated there. How about y of 0? Y of 0. This right-hand term will go to 0 because of the sign. The left-hand term will be e to the 0 times cosine of 0. That's 1. Okay, so all good on the initial conditions as well. All right, now for the rest of this, let's go back to my code for Euler. So what do I have to change here? Go back to the old step size. So 0.5, 13 steps. Differential equations are dx dt equals y and dy dt equals negative 10 times x minus 2 times y. All right, now run it again and pluck out the values that I actually want. Okay, so what do we want here? So for part B, at 2 seconds, we have negative 2 and 3.75. At 4 seconds, we have negative 7 and negative 25.9. And finally, at 6 seconds, we have 53.6 and negative 237. All right, so it seems like the y value, I mean, this didn't blow up. So these magnitudes didn't get as large as the last equations, the last system. But eventually it looks like the y values did start to run away from 0 pretty significantly. One thing I did not make sure is that I checked the initial values. Luckily, they're the same as they were. Okay, next thing I want to do is shrink the step size to 0.1, which means I need to look at more steps. 61. And that should be enough. Same equations. All right. Now what are we looking at? Okay, these look markedly different. All right, so at 2 seconds we have 0.018 and 0.327. At 4 seconds, we have 0.012 and 0.104. So again, I'm seeing stark differences between these two approximations. For these solutions, it looks like I am, look like my X and Y values are both diminishing. But for the step size I just had of 0.1, my Y values, my Y value got very large. X value got pretty large too. Now, before I go graph the real thing, let's talk about which of those makes sense. If we look at the solutions, or like the solutions we were given for X and Y, they both involve trigonometric terms, which those are going to oscillate indefinitely. The cosine 3t and the sine 3t, those are going to oscillate between -1 and 1 indefinitely. But what are the rest of those terms going to do? They're all exponential terms, and they're all raised to -t, which means they're going to decay. As time goes forward, those terms are going to basically act as they're going to be a multiplier of those trig functions whose limit is 0. So basically what we're going to be looking at here is something like an underdamped response. So because of that, I believe strongly that part C gives more faithful representations, and it should. I mean, one thing we've said before is that we expect when we use smaller step sizes for Euler's method that we get better results. So for f of x, 1/3 e to the -x sine 3x. So I'm already seeing this diminishing behavior. And then for g of x, e to the -x cosine 3x minus 1/3 e to the -x sine 3x. Okay, so the graph, even before I look at the numbers, the graph bears out what I thought would happen. So 6 seconds is as far as I wanted to go. I mean, I have to zoom in pretty far to see these separate at all. And when I do, they're very close to 0. So look at these scales. This first, like, thick black line here is, 0.02 and -0.02. So now let's look at the numerical values. At 2 seconds, the X and Y values I have are -0.012 and 0.145. I mean, my answers are not going to be far off just because, at least in part C, my answers are not going to be far off, but just because they're all going to be like very small in magnitude. They're all going to be very near 0. But for my Euler's method calculations, I'm kind of leaving it up to chance where the oscillations I'm approximating for are ending up. Because of this behavior, the behavior the solutions really have, I don't think I'm capturing it very well. So one thing I want to talk about is this. If we do have this trigonometric relationship, which is bounded, it just goes between -1 and 1, and that bounded relationship is multiplied by this decaying exponential function, which is not only bounded but decreasing, then how did I ever get these X and Y values that got really large? I think the way that happened is this. If we look at our differential equations, x prime equals y, and especially y prime equals -10x minus 2y, our first step probably got very far away from our initial condition. So our very first step had a dx dt value of 1, which means our dy dt step had an initial value of -10 times the initial value of x, which was 0, minus 2 times the initial value of y, which was 1. So the rates of change for dx/dt and dy/dt initially were high enough. They were significant enough to throw the rest of the calculations off. So yeah, we're seeing some dangers here. Even when we take really small step sizes, Euler's method can still, once you have a significant error in the early parts of the Euler method process, those can compound pretty rapidly. And we saw two good examples of that here. All right, that's all for this section. Moving on to the next one.